Good morning. We're going to get started with our Mountain Glaciers Dramatic Changes Caught on Film press conference. First speaking will be Michel Pachet from McGill University, Montreal, Quebec. He'll be followed by Gary Clark from the Earth and Ocean Sciences in the University of British Columbia in Vancouver. And last will be Uliana Hordowski from the Cooperative Institute for Research in Environmental Sciences at the University of Colorado in Boulder. Michel.
Thank you very much. So a quick introduction of our recent work. I would like to mention that this work is part of a larger multidisciplinary collaborative projects we have in Peru, working mainly on climate change's impact on water resources, both studying the physical side of it and the human side of it. But today I'm going to show you some recent results we have regarding water resources in the Cordillera Blanca. And what I'm going to explain to you or show to you is how we came to the conclusion that, in fact, the glaciers have started to lose their influence on water resources in the Rio Santa Valley, or in other words, that the water has, the region, has passed the peak in water in the Cordillera Blanca, meaning that even if the glaciers, or the retreat of the glaciers is accelerating, still accelerating in the Cordillera Blanca of Peru, the amount of water that the stream, like Rio Santa or its tributary, receives from the volume that is lost from the cryosphere there is decreasing and not increasing. And this is a bit, this is unlike what was thought or believed until recently. A few words on the setup. Here is a picture of the Rio Santa Valley that we have here in blue. In fact, this valley is a really good example of what happens at different places in the world with glacier-fed watershed hydrology. Where you have a significant mass of ice that supply water to driest region during dry period of the year. And here, why is that? Is this a good example? I would say because you have. I will try to make it working. Yeah, it works. You have headwater with glaciarized mountains. Here, for example, you have the Cordillera Blanca, which is the area of the world with the highest density of tropical glaciers. And this water flows down, reach local population that live mainly from traditional agriculture. And as we go downstream, we reach much more industrial use of that water, with here, for example, an old and very important hydroelectric plant. But even when we go south, we arrive to places where the precipitation are really, really low all along the year. We even speak about only 10 millimeters of water here in Chimbote. And this water become really, really valuable because there is no much precipitation, and it's highly diverted. This summer, for example, we went through the Rio Santa with a new system to measure the discharge, and the difference between that point before the main diversion and a point just above the estuary was 80%. So it means 80% of the water that came from the mountain was diverted mainly for agricultural, for irrigation, agricultural use. There is a huge project called Chavimochic that is still expanding, and that it's by itself taking 50% of the flow. An accelerating retreat, as I said, what we did is, we first of all use what has already been published, and there is a lot that has already been published about glacial cover in this area for many different watersheds, including La Balza, La Balza here, which represents in fact what we call the entire upper Rio Santa. And we have compared the different ice cover with time and calculated a percentage of annual retreat of the glaciers. And we did calculate that for 1930, 2009, and 1990, 2009. And what we see is that, first of all, these rates are quite impressive. These are in percentage, so it means that, for example, if you take Young Anuko, on the 80 last years, this watershed lost 1% of ice area per year, which is already very high figures. But if you see these figures only calculated on the last period, you realize that we observe an acceleration of the retreat of the glaciers in this area. So the idea we had is, thanks to this hydropower station I mentioned earlier, it has been some discharge measurements that have been conducted by the Peruvian government on the last 60 years. And we have had, with this data, we first of all worked to use only the ones that were of high quality enough. And we say, with this data we have, can we situate ourselves, or can we situate this bassin on the famous or already well-known curve, theoretical, conceptual curve of glacial retreat impact on water resources? Here I took the example of Milner in 2009, but in different publications we will find that. And say, can we make the relation between the concept and the reality? And for that, we took the data we had here, calculated for annual discharge, dry season discharge, and also flow variability that has been previously studied, like for example by Devin Collins, that did a lot of work on that. So we did study different parameters corresponding to this aspect of the discharge, and we did compile our data. It was a massive amount of data, took some time. And then we say, can we, and at the same time say, we will make some trend analysis. So here we use some statistical tools, like, for those who know, the Mann-Kendall regression, trend analysis, sorry. And at the same time, so we created a model that would reproduce this kind of curves, but especially for our environment and for the three parameters I talked about in parallel. That was not done yet. And say, maybe we can relate our records with this model that was tailored for our working area. And here is the result, synthesized here, is you find here a bit shaded the different curves that were produced by the models. And we have just put it here in red, what we call the peak water. So the peak water is this theoretical point that makes the transition between stream water, stream discharge that increased due to the glacial retreat, and the phase where the volumes of the glaciers become too small, and even if you get still an increase in the retreat, or in an acceleration of the retreat, it ends up leading to lower discharge. And what we have seen here is that for almost all the watersheds that we studied here, we had good evidence to say that we have passed the peak water, and especially here, La Balza, which represents the red line here, that drains the entire Rio Santa, was definitively in that group. So, first conclusion, nothing that I didn't mention already, says that we have passed the peak discharge. As a consequences, for dry season, we will get lower discharge and an increased variability in flows. And one exercise we did that with a complete glaciers disappearance at La Balza, this point that drains the entire upper Rio Santa, we may go down to 30% of the actual level for the dry season. Thank you.
Good morning. I have a handout which has the full title and author list at the back of the room, so I'll spare you a title slide. The concern of our work is the fate of glaciers in Western Canada, specifically those of the provinces of Alberta and British Columbia. This slide here shows distribution of ice in this part of the world and also the 10 regions that we divided the study area into. The climate varies, as you can imagine, from the coastal climate in the south to the dry, cool climate in the northeast. So we broke up sort of into climate zones and treat them separately. Today I'm reporting on 3 areas. That's the St. Elias up in the left corner, Northern Rockies, and Central Rockies. This looks like, well, so what? But actually the St. Elias has more ice area than all of the glaciers of the European Alps, and the Northern Rockies and Central Rockies together is all more glacier area than all of the Swiss Alps. So this is a big bite of glaciers. We're doing all of them, and actually we'll probably have it all done in several weeks' time, but I'll just report on the 3 that we've done. So the questions that we are interested in would be, first of all, what's the present volume of ice in these regions? And then what's the fate of this ice over the next, toward the end of this century? So we're projecting the glaciers forward in time. The volume question I can just summarize. We applied a new method to this and came up with a new estimate of the total volume of glaciers. I hope people can manage metric units, but the sea level equivalent of this volume is only 6.6 millimeters, not enough to worry anyone. However, the volume of ice here is something between 2,600 and 2,700 cubic kilometers. That's a very large volume of ice, and if most of it disappears, there will be extreme consequences for these regions. These stream flows will change, the timing of melt will change, the temperature of the streams will change, and these will have adverse impacts on tourism, on hydroelectric power generation, fisheries, agriculture, etc. So these are interesting questions with societal aspects. Now, what we've done in this work to do the projections to the future is rely heavily on the Intergovernmental Panel on Climate Change, who are the sort of international authority on projecting climate to the future. And they proposed, one of the big uncertainties in future climate is actually nothing to do with climate physics, but with human behavior. Will we be good citizens or bad citizens? So they have what they call emissions scenarios, and they essentially have a gradation of citizenship from pretty good to pretty bad. The A2, for example, is one that's considered pretty bad in terms of citizenship. That's reckless usage of carbon with little control on it. The B1 is the pretty good, and the A1B is sort of middle ground. Actually, human behavior outstrips the A2 at the moment, that we're doing worse than what they imagined bad guys would be like. So I'll show you what these projections look like. This is what we do. We actually model in a computer the ice distribution, and then we apply the climates that are prescribed by the IPCC global climate modeling experiments, and we do this for the emission scenarios and a range of different GCMs, as they're called, global climate models. And this climate model that we're using here is one from Germany called the ECOM model, which tends to be one of the intermediate ones in our results. It's not the worst case, it's not the best case, it's just typical. And the scenario we're running here is A1B, which is the kind of middle of the road one as well. So this is distribution of glaciers in that St. Elias region that I showed you in the northwest corner. You can see these ugly boundaries. If I could rework history a tiny bit, I would have Canada purchase Alaska, and then we'd have a much simpler picture here. But okay, so here we go. This is 1990. I'm going to flip through decadally to 2100, 2000. Just watch now. 2100. So here's before, here's after. That's it. So if we reduce that to graphs, you can see that for the St. Elias region, the 3 different scenarios predict loss of volume the one that looks like the least loss, these are cubic kilometers over time from 1900 to 2100. And you can see that we're going to lose the purplish thing is the kind of good guy one, and the red is the bad guy one. And you can see that we don't actually believe the purplish resembles anything like what the humans are going to be doing. So the ones to concentrate on are the green and the red, which suggests that about half the volume of ice will disappear in that particular region by 2100. That's the good news. The other areas we looked at are actually more alarming. For the northern Rockies, here's the distribution of ice right now. And if we look at the volume projections, you can see that by 2100, even the good guys and the bad guys, it all comes out the same, that the glaciers are almost all disappeared by 2100. For the central Rockies, here's the distribution of ice there at the present time. If we project that out to the future, well, a little bit left over. If you're a good guy, it's going to be maybe 20%. If you're more plausible, it's less than that, probably 5 or 10%. So we think that the story, as applied to the other regions, will not change. That really we're going to be witness over the next century of the mainly the disappearance of the glaciers of Western North America. Thanks.
All right, good morning. My name is Uliana, and I'm at the University of Colorado with Ceres. And I wanted to talk to you about superglacial lake changes spotted in the Himalaya. So this is me working on the Nongzumpa Glacier in Nepal. So this is on the border between Tibet to the north and Nepal to the south. And I'm working here at about 5,000 meters. And the glacier flows down here. Off of Choyoyu, which is the 6th highest mountain in the world. And so what I really wanted to do was install time-lapse cameras in order to document how these lakes change in real time. And now, the time-lapse cameras, there's 3 set up. Just like this, we have to rappel down and then drill into the rock to place the cameras, and they're powered by solar panels. And what I really wanted to do was document in real time how things are changing on the hour, through the days, through the seasons, to capture any of these changes, basically to offer an unprecedented view into how the glacial system works. So I liken it to taking the pulse of the glacier. We're doing this in the short term, and then since this is only, I'm in the middle of my 2nd year of the PhD, this is going to be going on for the long term as well. So after we set up these cameras, we all managed to capture a superglacial lake drain and refill in real time for the first time that was seen on a Himalayan glacier. So this is me standing here for scale, and this line here shows where the water was just 24 hours earlier. And then not only that, but we were also able to put a number on how much water was involved in this kind of drain event, and then how long it took for this lake to drain and fill. So this is Ang Phula, my Sherpa guide, who we were the only 2 working out in the field, and he's pointing where the water used to be just 24 hours earlier as well. And we use this inflatable raft to get around in the lakes to take some high-resolution imagery, as well as measure water depths, water temperatures, and also collect samples for chemical analysis. So why do we care in the Himalaya? Well, the climate is warming. With that comes melting glaciers. Most people, when they think about glaciers, thinking about them receding, but they also shrink vertically. And what we see on Nongzumpa is a lot of this is covered in very heavy debris, about 1 meter of rock cover with the ice below that. But in certain spots of the glacier, we actually have superglacial lakes that have formed. And these lakes can lead to enhanced melting of the glacial ice. How does that happen? Is when you form this lake, you actually have exposure of bare ice walls. We're going to see a picture of that next. So that bare ice can melt a lot faster and therefore lead to collapse in the vertical direction. And once you do that, you increase the amount of water in the lake and therefore can increase the amount of flooding that happens. And so the big picture is that leads to loss of life and infrastructure in the Sherpa valleys. So this is some imagery from one of my cameras looking at ice calving. So what that means is any ice that comes down and falls into the lake. So if you look here, you see this triangle that formed. The next image, it's gotten a lot bigger until finally a huge collapse. So I was actually about a half hour away from getting down to the glacier at this point. Luckily, was not in the boat at the time. This event resulted in 8 centimeters of overall water rise in this lake, which doesn't seem like a lot, but for one ice calving event to do that, and this is me again for scale with some of the ice chunks that came down. This is me at the start of the season, set up my instruments to measure the water levels, and this is at the end. So this is what I mean by when I say we have the potential for flooding. But not only that, we have the potential for drain. So I'm going to run this movie here. And I'll ask you to focus on this part of the image as well as around here. And move it over and start it. So watch here. And there it starts to go, exposing a huge ice wall here. And then the level starts to come back up very slowly. And so this is the boat here for scale, so you can get a sense of how large these lakes actually are. This one in just 3 years has grown to the size of 3 football fields. And then as far as putting numbers on it, in that first drainage event, we have a loss of about 50,000 cubic meters, 55,000 cubic meters the next day, and then it takes 5 days to gain back half of that amount. So there's a net water volume loss during this event. So the big question then is, well, did the glacier lose more water than normal? So typical meltwater runoff is about 40,000 cubic meters per day for this size glacier, which means 16 Olympic-sized swimming pools. One lake drainage event that we captured here on film is the equivalent of draining 42 Olympic-sized swimming pools. So one lake draining is more than double the normal runoff from the glacier. And the size of this glacier is 18 kilometers, and there's at least 200 of these kinds of superglacial lakes on its surface. So my future work, what this has revealed is I would really like to extend my camera network further up Glacier. That's where a lot of the action is happening. And further up so I can get a vantage point from multiple lakes. This is me trekking at about 5,400 meters to take a closer or a higher up view of the glacier below. And then also tracking communication between these lakes by linking up instruments to see if one lake drains, where does that water go? Where does it fill down the glacier? And how much of it actually runs off at the glacier's end? And these are my project collaborators and advisors. Thank you.
Thank you. Okay, we'll go ahead and take questions. And please state your name and affiliation. And also the speaker, if you could please say your name before you answer.
I am Harvey Leifert, freelance. It's for Uliana. I'm sorry I can't read your last name from here. But the refill of the lakes comes from what? The melting of the calved ice or new inflow or some other?
Right. So the refill is actually coming from higher up on the glacier. So if you think about the glacier like this, think about 2 bathtubs connected via a pipe. So the 2 bathtubs are the lakes. So if one starts to drain from higher up, it sends that water down to fill that one, and then that lake can send down its water. So it's a system, a network connected. So how do you actually initiate a drainage is you open up a crevasse, the water drains through because it's warmer than the ice, melts it, and sends that water down.
And just a general question for all of you, are these slides available somewhere? I know we can see them online, but is there a printout?
Yep. We have handouts in the back,
They're in
but
the
these
back.
can be made available
Okay,
to you.
thanks.
It's a question, sorry, Steve Connor from The Independent. It's a question for Michelle. In terms of this peak water event that you've monitored, could you just spell out in a little bit more detail what it would mean for the people living in that valley? And secondly, how unusual is this peak water? Do you expect other regions in South America, or indeed the world, to go through the same sort of process? And could you give us some sort of assessment as to how many peak water events we're likely to see over maybe the next decade or so?
Yeah, so for the first part of your question, the peak water, the point is to say, if we come back to what was conceptually accepted, with the fact that when your glacier starts to retreat, it produces the storage of the water will increase the discharge until you reach a point where the surface of your glacier becomes too small to sustain that increase in discharge. So what you get is a plateau, and as from the plateau you have a decrease. So now, what does that mean? First of all, the first point is to say, I remember a conversation we had 2 years ago with the head of the glaciological office at the Office of Glaciology at Huaraz, and I was surprised because that person told me, yeah, we know that we'll reach the peak water within something between 10, 20, or even 40 years. So we should start having some good adaptation measure to make sure that it will not hurt. So what it means now for the population is that instead of having 10, 20, 30 years perspective to find some solution for water use, water allocation, in fact, these years do not exist. And with glacial retreat, the impact of the glacier, independent less of the precipitation, will make that, in fact, on average, year after year, they will get less water during the dry season in the stream.
Okay.
On the second part of the question, I don't remember, sorry.
Yeah, it's just to broaden it out away from that one particular glacier. What about other glaciers in South America and indeed the world? I mean, what's the situation regarding peak water there?
Yeah. So, of course, it's difficult for me to answer specifically to that question. What I can say is that the problematic of glacial retreat on water resources is really hot in South America. We know that in Bolivia we have started to work with NASA on a similar project. We know that there are also other watersheds affected in Peru, in Ecuador, in northern Chile. But as you know, this is also a very hot issue in the Himalayan when you have the famous Indus irrigation system, which is, I think, the largest in the world, that's fed partially by the meltwater, and this a decrease in discharge from this river could have a very, very high impact.
Okay, do you, Kate?
We have a two-part question from the webcast. This is from Seth at the Associated Press. For Michelle, today in Chile they announced that the Morning Glacier retreated 1 kilometer, more than half a mile, between February 2010 and January 2011. That's in the southern Patagonian field. How does that compare with the Peruvian glaciers that you've seen? And how does that compare to other glaciers around the world?
I would say that, first of all, these figures is quite exceptional. I mean, I think you speak about time span of 2 years or something like that, or less than 2 years, 1 kilometer. I mean, this kind of figures taken individually are not something we can really use because it could be related to many different parameters that are local. What we see more in the tropical Andes is a steady but accelerating retreat of the glacier. We don't speak about kilometers of ice lost, but we know, and we can even observe that when we go on the field. We have to say that after a few years, we realize that we have to hike a bit more to reach the glacier because they decrease. So I would say that we are probably in a less dramatic kind of situation as the one you describe, but on another hand, on the long term, the retreat has been quite enormous.
And then I guess for all of you on the panel, can you kind of put the speed of glacial melt in context? Like, what's the fastest in the globe? Is it in Greenland? Can we put the individual glaciers that you talked about in perspective to a world average and the fastest and slowest in terms of speed?
That's a challenging question. I think, first of all, Greenland is not, even though we're most concerned about the future of Greenland, the melting isn't what's going on there. At least it's not surface melting. There's obvious surface melting mapped every year, and it gets larger and larger, the zone of melting. But the main mass loss there is from breaking ice off the edges and into the ocean. So it's a different mechanism of shrinkage from the usual ones in the mountain glaciers. The answer to your question about where in the world the record is, I really don't think we have an answer to that. Someone may, but it's someplace in South America or Himalayas, I would certainly guess.
I would say with the Himalayan glaciers are unique in as far as they're covered in very heavy debris cover. So for example, for Nongzumpa here, the lower kilometer or lower 5 kilometers of the glacier could be considered almost stagnant because the debris cover is so thick that you're not melting the ice any longer. The melting is actually happening higher up on the glacier. And so when you melt higher up on the glacier, you're starting to deflate in the vertical direction. So the wastage below debris cover is a lot slower than the wastage on bare ice walls surrounding these lakes. And this is why the lakes are really important. We're seeing a lot of these lakes forming across the Himalaya. And because they're exposed ice walls, the rate of melt is twice as fast on them. So you can really aggravate the process through these lakes.
Could I say something about debris cover? Essentially, it slows down the rate of disappearance of ice, but it's not something that gives you much comfort because this ice is essentially hermetically isolated. You don't see it, and it's not contributing to the water cycle. It's just gone. It's hidden. So it's not a comforting idea. It'll slow down the rate of sea level rise. You could draw comfort from that. But as far as participating in any other thing, you don't see it, and it's not visibly contributing to the water system.
So if forming loss is about 25 meters a day, do any of you know of any that are faster than that?
It's really difficult to answer that kind of question on typical cases because you have some kind of glaciers, like you take surging glaciers that will retreat during, I don't know, 15, 30 years, and then suddenly they will start advancing at an incredibly high speed. If we try to compare this kind of glaciers with other kind of glaciers, like the hanging glaciers we have in the Andes, we'll have really difficulties to make. What I think what is really important is to accept that at local scale you will find some very particular cases. You even find some glaciers that have gained mass or that still gain mass in the cryosphere, and we have to say that. But each time you have a phenomenon like that, it's really good to go in details to understand why. I will take the example of, for example, the Norwegian glaciers of the coast, the west coast. During the 90s, they did gain mass significantly, and nobody discussed that. And this example has even been taken by people who were trying to say that climate change did not exist, saying, oh, you say the glaciers are receding, but go to Norway, you will see they gain mass. But in fact, this was a temporal impact of climate change, where they did get an increase in precipitation, while the increase in temperature was not high enough to compensate for that. But after a certain point, they reached a threshold, and these glaciers have started to retreat really, really fast. So you have some local phenomenon that need to be studied locally, and you can see the global picture and see that, of course, as we all know, globally we are losing a very high amount of ice on the Earth, and this is accelerating.
Rick Lovett, freelance. This is also for Michelle. I'm wondering whether or not, can you explain how you measured yeah, you probably did, but I couldn't catch it in the slides. In common language, how did you measure that it has peaked? And I mean, I presume it was curve fitting to something. And also, my understanding of this total precipitation isn't changing, so, right? So this is a change in cycle. So in theory, big dams would solve it also.
Multi aspects in the question. I will first of all answer the last one first to confuse you. The point is when we say, yeah, if precipitation are not changing on a yearly basis, you will not get any change. So this is partly true. This is true that with this kind of phenomenon, what we see is a huge change between the seasons. So at high flows, you get more water, and at low flows, you get less water. So this makes really critical this period of the year. But I say it's only partly true, because with a landscape or watershed with glaciers, you have some energy effects that make that your watershed that has some glaciers will capture less energy from the sun than a non-glacial watershed. This means that when you remove the glaciers, you have more evaporation. And if you build dam, you even increase this phenomenon, because we know that the evaporation from reservoir is much, much higher than what we can get sublimation from the glaciers. And this is significant. So dam, of course, can be seen as a solution for some very particular projects, but we have to know that these dams will never ever replace the hydrological systems that are in place today, with the glaciers releasing slowly the water during the dry period and accumulating it during the wet period. And again, I forget the first part of the question. Yeah, the measurements. We have several kinds of measurements. For the ice cover, we use what was, as I said, published in the literature, that was based on aerial pictures, but more recently, of course, we use now satellite pictures. So the last data I showed, which are 2009, were based on the raster imageries. We just compare the situation between different years and see how it was a change. On a hydrological point of view, we have discharge stations. So we use historical data. So these stations were in place a long time ago. What we did is also we rehabilitate some of those to keep monitoring the situation. And the way it works is that mainly you measure the evolution of the level of the river. And by measuring the level of the river, you can translate that into a volume. And that's the way it works. I hope it's answers.
So it's a combination of ice cover measures and gauging stations.
Yeah, exactly.
Zoe Corbin, freelance for Nature Climate Change. I have a question for Uliana. You saying that you're seeing a lot of these lakes forming, and you have about 200 now. How does that compare with the number you had previously, and how does it change seasonally? And I have a kind of second question as well, separately, which is the use of the time-lapse photography, and has that been used before?
So for the first part, as far as the lakes go, So there is a group that has worked on this glacier for the past decade. So I chose this glacier specifically because there is some historical data there. So looking at patterns of how these surface areas have changed, they fluctuate. Sometimes the lakes drain a lot, sometimes they get a lot larger. Overall, and just in the past 3 years, this one lake that had that big drain event went from the size of 1 football field in square meters to three football fields. So as far as time-lapse being used before, so there is James Baylog's Extreme Ice Survey looking at the termini of glaciers, for example, in Greenland, in Iceland, and across other regions of the world, specifically looking though at the terminus. Now I'm using time-lapse in particular to target these lakes. And the reason why is when you see this video footage, you see this lake drain, then you see it refill. Say I came a week before that happened and a week after, the lake level is the same, right? It hasn't changed, but my imagery tells me something happened. 42 Olympic-sized swimming pools got sent down the glacier. That's something that we wouldn't have known if we didn't see that footage, because it looks like nothing changed. So this is a way to monitor in real time, to actually look at, over the long term, how do these changes correlate with things like precipitation? When, how much rain are we getting? How much snowfall are we getting? And also, as far as when does the melt season actually start? Is it the same every year? Does it start sooner or later? These cameras can provide that information to you in the longer term. Because I think that's what's most important, is you're, like I said, trying to take the pulse of this glacier in the short term and then forecasting into the future in the longer term. So you have to understand how this system is working, and this is, I feel, a great way to do that.
Do we have any more questions from the audience here? Any more questions from online, Kate?
Yeah, and the answer is no, but we can put something up online. But Jody from NASA was asking if the time-lapse of the Himalayan glacier is available at the Hemisphere's website.
It's in development, and the reason why is because my Sherpa guide has said he is going to go back to the region in a few weeks to pick up more photos, and so I want to create a longer-term movie. This is just what was captured at the time I was there, so I'm still waiting to do that. But.
Are there any more questions?
Harvey Leifert, Freelance again. Just a quick question. What is the interval between the shots in your time-lapse?
It's every hour. There's multiple options you can choose. So it does shoot through the night, but I turned off the flash to conserve any of the power. Ideally, it's supposed to do IR, infrared. So one of my future projects might be installing thermal cameras to actually look at how the lake temperatures are changing too. Because some of these lakes are very, very cold, around 2 degrees centigrade. Some of the other ones are around 5 degrees centigrade. And so I have a poster on Friday, if people are still around, where I explain some of the implications of that work and some of the chemistry that I found from those lakes, lake waters.
And Rick Lovett again, Freelance. You've been saying some of this, but can you summarize what has been the time change in the number of these lakes in the time this glacier has been observed?
They've been increasing as far as in number. And also as far as surface area changes. So they are getting larger. I guess the best way to put it is you could think of these lakes as being cancers that are consuming the glacier. And again, the point of doing the time-lapse was getting a number on how fast is this happening, because the drain can happen very quickly, but the refill takes a lot longer. So that tells you something about the workings of the glacier. And then how much volume are you sending down? When you put it into that perspective with Olympic-sized pools, you can see it's a vast amount of water that's leaving the system. So.
Okay, thank you. Thank you to the speakers. Our next press conference will begin at 11 a.m.